Okay, so this video is going to go over topic 10 for EGCE201 statics. In topic 10, we're going to discuss moment of inertia, and we're going to develop a method for determining the moment of inertia of any area. Okay, so let's start by first understanding what moment of inertia is. So whenever we have a distributed load, like the one shown here on the outside, these black arrows, that acts perpendicular to an area. So this area dA is a small little area that you can see that's been highlighted. So we have these black arrows that act perpendicular, right, to this area. And when the intensity of this load varies linearly, the calculation of the moment of the loading about an axis will involve an integral, okay? So if we want to calculate the moment of this load about some axis, right, we're going to have to take the integral of this distance y squared times the area, okay? So if we want to see how this works, let's look at this figure. We have a plate that is submerged in a fluid, right? So this is underneath the fluid, and it's subjected to this pressure P, which acts perpendicular to the surface of that area. The pressure is varying linearly with the depth, right? Because as we increase the depth, the pressure increases. There's more fluid on top, okay? And we're going to say that gamma is the specific weight of the fluid. Right, pressure is equal to gamma times y. So the force acting on this differential area dA, I'm gonna erase some things here and highlight this differential area dA. If you take this little strip here, okay, is going to be dF, this resultant force here acting on that area, which is the pressure, is to be equal to the pressure P, right, times that distribution over the area. Pressure times area, force is equal to that, right? Now, if we substitute gamma times y into this equation, we have, for pressure, we have gamma times y for the pressure, and then we still have distributed over that entire area, dA. But then if we want to take the moment of this force, dF, right, this is a force. So the moment of dF, okay, we would say that dm is equal to y times df, right, the moment arm. And if we plug that in, we would get gamma y squared dA. Okay, this is about the x-axis, right? That's why we're measuring that moment arm y. Okay, and we can simplify this as the moment, if we integrate, we get the moment is equal to gamma, which is a constant for that fluid, integral of y squared dA, right? This is the function that we use for the calculation of moment of inertia, okay? Now, this portion here under the integral, try to box it over here. This portion here, we call this the second moment, okay, of area about an axis. Okay, and this is equal to the moment of inertia. That is the definition. Okay, so what does this word inertia mean? Why is it used? This word inertia is used because formulations similar to mass moment of inertia, which is integral of y squared dm, right? If you remember, this is mass moment of inertia. So we use a similar terminology for any type of moment of inertia. This is called mass moment of inertia, right? And note, for an area, this integral has no physical meaning, but it is used in fluid mechanics, mechanics of materials, structural analysis, and mechanical design to help us in different calculations. Okay, so let's continue here. And moment of inertia of a different differential area dA about the x and y axes is what we just derived. So we just derived these two, well, we derived this one, but of course now if you want to derive this for the y-axis, you're going to use the moment arm of x squared instead. So you're going to use the distance that that shape or that area is from the y-axis now. So you're going to be using that x moment arm, okay? And you can also formulate this dA for a pole, and this is called the polar moment of inertia, and we use the symbol J to represent the polar moment of inertia, which we'll use in mechanics of materials when we discuss torsion or twisting. Okay. Now, the relationship between the polar moment of inertia, the moment of inertia about the x-axis, and the moment of inertia about the y-axis can be formulated using r squared equals x squared plus y squared, and you can think about this as the formulation for polar coordinates, right? This is the same relationship that you would use to go from polar to Cartesian coordinate system, which is exactly what we're doing here, okay? All right, so one of the most important theorems that we'll use in this class and your future classes is called the parallel axis theorem. This theorem allows us to find the moment of inertia about any axis. So if you recall in this last slide, we're finding moments of inertia about the x and the y axis specifically. But what if we need the moment of inertia about a different axis that is not this x or this y, just some other axis? We can use parallel axis theorem to help us find the moment of inertia about any axis that is parallel to an axis passing through the centroid and about which the moment of inertia is known. So what does that mean? Basically, if we know the moment of inertia about another axis, and this axis is parallel and passes through the centroid, we can use the parallel axis theorem to find that moment of inertia. Okay, so to derive this, come over here for a second and draw this. So to derive this, let's consider this shaded area here, this shaded blue area. Okay, if we want to find the moment of inertia about the x-axis, we would choose this differential element dA. Okay, and this dA is located at some arbitrary distance y prime, some arbitrary distance x prime from the x prime y prime axes. Okay, this is our centroidal axis, so this is the centroid of the element. That's why we have the x prime and y prime axes pass through the centroid. And we know how to calculate the centroid now from our previous topic in this class. Okay. If the distance between the parallel x and x prime axes, so do we see how this x prime axis, the axis that passes through the center, is parallel to the x axis, right? And the distance is dy. Here, this distance between the x and the x prime axis is dy. Okay, then the moment of inertia of dA, the moment of inertia of this dA, it's a differential, right? Because it's a differential area. So the moment of inertia of dA about the x-axis is the differential of Ix about the x-axis, which would be this y prime plus the dy, that full distance away from the x-axis, right? Because we need this total distance. We can pick a different highlight. We need the total distance away from the x-axis, which would be y prime plus dy, okay? And then we would take the dA, right? And then for the entire area, this is just for the differential area. What would we do for the entire area? Well, we integrate, right? We integrate to get the whole area. So we would get Ix is equal to the integral across the whole area of y prime plus dy squared dA. And if we want to simplify this further, we would integrate over the entire area. We'd have y prime squared dA plus, I'm foiling this out, right? 2 dy integral of a y prime dA plus dy squared integral of a dA. I'm taking out dy because it's a constant here, okay? And this is our first, this first integral that we took, right? We integrated once. This first integral, okay, this is equal to the moment of inertia of the area about the centroidal x prime axis, right? So this is equal to the moment of inertia of the area about the centroidal axis, which we would call Ix prime. Okay. And let's say we take the second integral now. We take another integral. Okay. That's going to equal 0 since the x prime axis passes through the area centroid. So what we would have was we would have the integral of y prime dA, which is equal to y prime bar integral of dA, passes through the centroid, right? Y prime is 0. So this has to be 0 if we were going to take that second integral, okay? Now our third integral, right, so this is the first integral. Let me box these. This is the first integral. The second integral is this one, which is 0. This third integral is where things get important. This one right here. So just to make this clear, we're not taking multiple integrals. I'm talking about this first integral in the orange box, second integral in the red box, third integral in the pink box, and so on. That's what I'm talking about here. This represents the total area A, right? So we would have Ix is equal to Ix prime plus a dy squared, and Iy equals Iy prime plus a dx squared, okay? And these two findings are super important. These are parallel axis theorem. This third integral is where stuff gets really interesting, okay? And for our polar moment of inertia, we have J equals Ix prime plus Iy prime, okay? And we know d squared equals dx squared plus dy squared. So we can simplify this as J about any axis is equal to J about the centroid, this is about the centroid, plus AD squared. So we can do this also for the polar moment of inertia, to find the polar moment of inertia about an axis that does not pass through the center, just like we can for the moment of inertia about the x and y. The form of these three equations basically states that the moment of inertia for an area about an axis is equal to the moment of inertia about a parallel axis that passes through the centroid plus this AD squared. Okay, what is d? We're going to talk about this more, but this is the perpendicular distance between the axes. Okay. Now, the radius of gyration, okay, this is equal to our radial distance to a point, which would have a moment of inertia equal to the body's actual distribution of mass if the total mass of the body were concentrated at that point. So what does that mean? We have these formulas here for radius of gyration, but let's kind of draw this out so we can better understand what this is saying. So let's say I have some object here. Okay, I'm going to highlight this object. It has some okay, some shaded area. And let's say this is our centroid, our point O, okay. And we have some m, this is our mass moment of inertia, okay, and we have some rotation here. So our mass moment of inertia of the real object of the whole object, right? This whole real object is equal to moment of inertia about 0.0, okay? But now let's assume that this whole shape, okay, this whole mass of the object is concentrated at this teeny tiny point M. Okay, this whole mass, let's see if I can highlight this. So I just took that whole blue mass and I concentrated it. So we write this down. So let's now assume this whole mass is concentrated at this one point, this one tiny point here, okay? This one little point, we'll call it M. We still have our center O here. And now we have some distance from the center to this little lumped mass M. We're going to call this R, okay? And we want to answer our question here, at what distance R is the mass moment of inertia the same, okay, for this first object and the second object, okay? This radius of gyration, R, is what we're calculating here, okay? We use this often in the design of columns in structural mechanics, radius of gyration, okay? So let's talk about the procedure for analysis. In most cases, okay, we can determine our moment of inertia by using a single integration, okay? So this is procedure for moment of inertia and everything we're talking about so far. So in most cases, we can use a single integration, and we have two ways of analysis. Okay, so we're going to have a curve defining a boundary of area, such as y equals f of x. And what we're going to do is we're going to select a rectangular differential element with some finite length and width. Okay, so let me show you what I mean by this. Say we have our y-axis, we have our x-axis. We have some curve, y equals f of x. And we have this shaded area here. Okay, so what we're going to do is we're going to select an area, a rectangular differential element. Okay, so let's say this little rectangular differential element. Okay, and this element hits here at some point x, y, some coordinate point. Let me kind of highlight this. Okay, and this element has some area, dA, right? It has some center point, right? We know that we're saying the center point here that I just drew. Get the line, there we go. This is at some y, right? This is that coordinate point. This is at some x. And this element has a thickness of dy. Okay. So our case one here is that we orient the element so that it's parallel to the axis about which this moment of inertia is computed. So if we have Ix, we want to orient the element like this so that it's parallel to Ix, okay? So this solution occurs when the rectangular element, this red element, is used to determine Ix because it's parallel to Ix. So we're going to use Ix is equal to y squared dA, okay? So we're going to use case 1 for Ix. You could probably imagine what we're going to do for case 2. Probably should have copied that before I drew all over it, but we'll have to just redraw it. Let's see if I can, let's see how messy this will look if I draw right over it. So let's do case 2 right here instead of redrawing all this. So case 2 here, you can see I would orient this element parallel to the y-axis. So this is when I want to find Iy, right? And now my x would be, I'm going to use different colors here. This distance. My y would be this distance, and this would be my dA, right? And this is when we want to find Iy. Okay, so we have two different options here. All right, so let's try an example of this. I promise these are not that complex, and I'll tell you which ones to kind of focus on, but these get a lot simpler once we kind of just start doing the problem. So we have example 1 here, and we want to determine the moment of inertia for the rectangular area shown in this figure with respect to A, the centroidal axis x prime, B, xb passing through the base of the rectangle, and this got a little cut off, but the pole or z prime axis perpendicular to, let's see, this is part C. So this would be the polar moment of inertia passing through the centroid C. Okay, this is a perpendicular axis. So let's start with part A, the centroidal axis x prime, okay? So the entire element is at a distance y prime from the x prime axis, right? So this is our x prime axis, and we want to find the moment of inertia of just this rectangular area, which acts at a distance y prime from the x prime axis. So we need to integrate, okay, from y prime equals negative h over 2, right, to a y prime value equal to h over 2, right, along that whole area. And this dA is equal to b, that width on the bottom, times dy prime. Okay, so we're going to plug this into our integral here, and we have moment of inertia is the integral about a, y prime squared dA equals integral negative h over 2 to h over 2, y prime squared times b dy prime. And if we simplify this, we can take the base out, and we have y prime squared dy, and we end up getting that this moment of inertia is equal to 1 over 12th bh cubed. Okay, now I'm gonna square this off. This is very important. This, we just derived the moment of inertia of any rectangle, so you no longer have to rederive that. Any rectangle's moment of inertia, okay, about the x-axis, about one axis, so far is going to be 1 over 12 bh cubed. If you want the other axis, you're going to switch the b and h's. So let me show you what I mean by that. If we have a rectangle and this is 8 inches, height is 12 inches, Ix is equal to 1 over 12, 8 times 12 cubed. That is always, we just derived, moment of inertia of a rectangle. Moment of inertia, I'm going to abbreviate as MOI. of a rectangle, okay? All right, so the next question is the axis XB. So the axis XB is down here. It's not through the centroid, but it's parallel to X prime. So we can use the parallel axis theorem now. Right? So we can say that moment of inertia about this axis XB, which is parallel, is equal to a parallel moment of inertia plus a times the distance, that perpendicular distance squared. So we're going to use the 1 over 12 BH cubed plus the area BH times the y squared. What is the distance from this parallel axis to the next parallel axis? What's this distance? H over 2. That's it. Okay, and if we simplify this, we get 1/3 BH cubed. Okay, so this is always for rectangles for an axis parallel to the one passing through your centroid. You can use this 1/3 BH cubed. Okay, and for the last part, we want the polar moment of inertia. We need to get IY, right? Because we need to add those together. Okay, all we have to do for IY is switch the dimensions. So IY is also equal to 1 over 12 HB cubed instead of BH cubed, right? We're just flipping the axes. Okay, so we can really easily get the polar moment of inertia now. Okay, and we can plug all this in and we get 1 over 12 area times h squared plus b squared. And this is the polar moment of inertia for any rectangular shape that you, again, don't have to derive again. Okay. All right, let's do another example. Okay, this is going to be a case 1 example. This was a case 1 example because we have the element oriented like we have here for case 1 in the X. We're going to do a case 1 and a case 2 next. Okay, so example 2, let's determine the moment of inertia for the shaded area shown here about the x-axis. It's case 1 because we're looking for IX. Okay, this differential area dA is equal to 100 minus x, I'm just getting the area of that shape, times dy, the thickness of the element. So if we plug this into our Ix equation, integrate over a, y squared dA, that's our equation. Let's plug everything in now. We get is equal to the integral from 0 to 200, right? 0 all the way to the boundary of y, so all the way over that element, y squared times 100 minus x dy. And now we need to further simplify this so that it looks like an integral that we can actually solve for. So we're going to plug in. We know that y squared is 400x. So we can plug that in here and we get 100 minus y squared over 100 dy. And then we can further simplify this as the integral from 0 to 200 of 100 y squared minus y to the 4th over 400 dy, if we plug everything in, and we can solve for Ix. You can use your calculators for this. And that's our answer. All you have to do is plug into those equations. Let's go ahead and do this for case 2 where we're looking for an IY. This is the differential element parallel to the y-axis now. And now all points on the element, this is the problem here, they don't lie the same distance from the x-axis. So we have to use parallel axis theorem for this one. Okay, not all points lie the same distance away from the x-axis, right? Okay, so let's go ahead and look at this rectangle. For this rectangle, our base is B. Okay, and our height is h. And we want our Ix prime, which is equal to 1 over 12 BH cubed. See this from example 1, we derived it. So our base in this case is our dx, our h is y for this element, and the centroid of the element is at y over 2 from the x-axis, right? So the moment of inertia about this axis, our dix, would be dix bar plus d a y bar squared. Okay, so if we plug everything in here, we have 1 over 12 for the rectangle, and then we have the dx times b cubed, no, bh cubed, sorry, h cubed, plus now our y dx times y over 2 squared. And if we simplify this, we get 1 over 3 y cubed dx. This is also a result we got from example 1. Right? This is for another axis. So all we have to do now to get our final ix is the integral of the distance d times ix, which is equal to the integral from 0 to 100, 1/3 y cubed dx. And we're going to plug in the value for y because we're integrating over x here. So we need to plug in this function here, 400x to the 3/2 dx. And if we plug this result into our calculator, we get 107 times 10 to the 6 millimeters to the 4th. So we got the same answer that we got in the previous, well, same example, but case 1, case 2. So case 1 was obviously way easier, right? So it's much easier to use an element that's oriented parallel to the axis you're trying to find the moment of inertia of. Okay, then you don't have to use parallel axis theorem. If you pick an element like this, you'd have to use parallel axis theorem because it's perpendicular to the axis we're trying to find the moment of inertia of. Okay, so let's move on to a really common type of problem in engineering applications. We're dealing with cross sections of beams or kind of shapes that aren't symmetric sometimes about both axes. So the next couple of examples we're going to do are going to kind of discuss those really common engineering shapes. So here we have a T-beam. We call this a T-beam because the cross section of the beam looks like a T. Okay, we want to determine y bar, which locates a centroid for the cross section, and then find ix prime. So this is a problem that combines topics 9 and 10, so it's a really good problem. What I like to do when I'm solving these is I like to redraw the problem here because I'm going to be marking up the cross section quite a bit. So I'm going to redraw everything here. At the top I have 150 millimeters, then I have 20, then I have 150, then I have another 20. Okay. The first thing I need to do is I need to find y bar, and we've done this in the previous section, so I'm going to go through this one a little quicker. Okay. So my y bar can be measured from the top or the bottom. I'm going to calculate my y bar from the top this time. So remember that means my datum is up here on the top. Okay. So I'm going to separate this shape into two areas. Area 1, this pink bar up top, and area 2, this green shaded portion on the bottom. Okay. Now area 1 here is 150 times 20, which we get 3,000 millimeters squared. And my y1 bar is equal to the distance from the middle of that portion, area 1, to my datum, which is just half of 20, so 10 millimeters. Now, area 2 we have A2, which is also 150 times 20. And then we have y bar 2, which is the distance from the middle of area 2 to the datum. So we're going to have 20 plus half of 150. So we get 92. Okay. All right. Now let's go ahead and calculate y bar, which is the sum of AYI divided by the sum of A. And we get y bar equals, I'm going to write this all out actually, 3,000 times 10 plus 3,000 times 92 divided by 3,000 plus 3,000, and we get 51 millimeters from the top. Okay, now our IX is equal to the 1 over 12 B1 H1 cubed plus parallel axis, right? Plus the second area, 1 over 12 B2 H2 cubed plus parallel axis, okay? This here is area 1. This here is for area 2. Okay, so the really tricky part about this is just having to find these distances D. Okay, other than that, it's pretty straightforward. So let's come back up here and let's work on finding these distances D. Okay, so what is the distance D, D1? Okay, I'm gonna kind of erase some information here. Let's see where I can. Okay, and I don't want this bar there either. Okay, so what is D1? D1 is the distance from the center of 1 to the centroid of the whole shape, right? This is what I'm looking for, D1. How can I find that? Well, I know that y bar is 51 millimeters. So if I know that this total distance here, if I know that this total distance from here to here is 51, and I just want the green portion, I just have to subtract this little 10 from here to here. I just have to subtract the 10. So my D1 is 41 millimeters. So I'm going to come actually here, put D1 is 41. Now I'm going to erase that so I can find D2. Okay, D2 is the distance from the center of area 2 to the NA. So I'm looking for this. Right? So if the center of area 2, the whole thing is 150, from the bottom, it's 150 divided by 2, right? So we have 150 divided by 2, which is 75. But I need to add, actually that's also this distance here, this whole distance. I should put, this is also 75 millimeters. So I'm going to take the 75, right? I want to find just the distance to the NA, so I'm going to subtract my y bar. So 75 minus 51, right? It gives me that little tiny distance, D2. Oh, whoops, actually, no, sorry. Not minus 51, minus, okay, let's do this again because this looks messy for me too. Let's redo this. Okay. So we want the center, I should have erased that, center here. So this is the D2 that we want, right? Okay. The whole shape's height, running out of colors, the whole shape's height, let's see, is 20 plus 150. So we have 170. Okay. Now, let's see how we can get this little D2. We can do, from here to here, we have y bar equals 51. Okay, here we go. So if there is 51, then this distance would be 170 minus 51, which is 119, minus half of shape 2, which is 75. So 119 minus 75 gives us 44. So you kind of just have to play around with those lengths. Okay, now we have enough info to plug into these two equations here. So we have Ix prime equals 1 over 12 base of area 1 was 150, height 20 cubed, plus area 150 times 20 times d1 squared. That's the first red square, triangle. Now plus 1 over 12, base of the second area, 20 times 150 cubed, plus the area 150 times 20 times 44 squared, and we can get Ix prime equals 1.658 times 10 to the 6 millimeters to the 4th. There we go. Okay. All right. Let's do another example. I think we have a few more and then we're done here. Okay. So I'm going to draw a shape here. Okay. And let's determine y bar, Ix prime, Ix, and Iy for this shape. So we have quite a few calculations to do. Okay. And we're going to say that our x prime is located right here at the center. Okay, and of course, where do we find the center point? Well, that's y bar, so we have to calculate that center point. Right, now let me give some dimensions to this. So we're going to have, let's do green. We'll have 200, we'll have, I know these dimensions are really off, but we'll say this is 100. And then we'll have 50 on this side, 50 on this side, and then this whole distance is 300, let's say. Ignore that this is not drawn to scale, obviously. Okay, so again, let's separate this into area 1 and 2. I'm probably going to shade with some different colors here because things are getting a little messy on these diagrams. So we have area 1 and area 2. Area 1, let's get our area. 100 times 300, so we have 3,000. And then we have our y1, which would be distance from the middle of that section to our datum. We're going to do the datum at the bottom now. Okay, which would be 250 millimeters. Just count that out. Area 2, we would have area, which is 200 times 100, which is 2,000. And we'd have y2, which would be the center, basically from this x here down, which would just be that 50. Okay. Our y bar is equal to the sum of the areas times y divided by the sum of the areas, so that would give us 170 millimeters. Okay. Okay, now for our Ix prime, right? We want the moment of inertia. We got y bar. We're done with this. Let's do Ix prime. So Ix prime is going to be a very similar calculation to the problem we had done previously. We just need to find our D1 and our D2. Okay, so if we know that our y bar, I'm going to replace this with 170 here. Okay, our D1 is going to be the distance from the center of this area 1 to the neutral axis. So this little y1, D1, D1, that distance there. Okay. Now, How do I get that little distance? Well, I know that up until this point is 170, and up until the top here, I would have the total length minus 170. Okay, so what's that total length? 300, 400, right? So 400 minus 170, I would have 230 here. Okay, and to get that little D1, okay, let's see, we can take half of the shape. So from here to here is 150. So that would be 230 minus 150. And our D1 would be 80. Okay, now for our D2, we need the distance from the center of the second shape to this axis we're trying to calculate the moment of inertia about, right? So that would just be 170 minus half of this, which is 50, so 120. This is our D2, okay? Now we're ready to plug everything in. B h cubed plus 100 times 300 times 80 squared. This is 80 squared plus 1 over 12 times 200 times 100 cubed plus 200 times 100 times 120 squared. And we get this really big number of 721,666,666.7. So to simplify this, we can write 722 times 10 to the 6 millimeters to the 4th. Okay, so we've now done one of these. We have a few more left. We just did Ix prime. Our Ix is actually not so bad, right? We just want to find the moment of inertia about this x, which is at the bottom here. Oh, actually, I should have drawn the x at the bottom here. Let's move. Our x is actually here, very bottom. Okay. So we want to find the moment of inertia now about the x. Okay. And what we can do is we can just move, basically use parallel axis theorem to move what we just calculated for x bar and move that down. So I'm going to redo the calculation so you guys can see this one more time. Okay, let me copy and paste this image. Okay, so if we want the moment of inertia now about the x-axis, we're going to do the same thing. We have 1 over 12, 100 times 300 cubed. This is the same as what we had previously. And then also plus the 100 times 300, but now times our d squared, which changes. What is our d squared now? Well, if we're trying to get to the x-axis, we need to go from the middle of this shape to not x prime, but all the way to the x-axis. So this d is now 250 squared, okay? So make sure you can calculate these now that we've done this a couple of times. Now the second area, 1 over 12 times 200 times 100 cubed, plus the area 200 times 100 times the distance now from the middle of this shape to the x-axis is just 50. And we get Ix equals 2.17 times 10 to the 6 millimeters to the 4th. Okay. Last calculation is Iy, which is actually our simplest calculation because our y is symmetric and in the middle. So for our Iy, we don't have to move any axes. It's already directly along the axis. So all we have to do is add the moment of inertias of both shapes. Area 1 and area 2. No parallel axis theorem because it's already at the center. So we get 91.7 times 10 to the 6 millimeters to the fourth for IY. Okay, so let's go ahead and do one more example. Okay. We want to determine the moment of inertia about the x-axis for this one, okay? Now, this shape is also a really common shape in engineering. I'm going to redraw our cross-section here because I like, again, marking it up. And this procedure is exactly the same. We just have to add one more shape in our calculations. Than what we had previously, okay? So we have 300. We have 20. I'm going to actually just take out the millimeters so this looks a little bit cleaner on here. And then we also have 20 from here to here. Nice thing is we don't have to calculate y bar for this because it's symmetric. So our y bar acts in the middle of the section. Right? The whole thing is 400, so it acts at 200 millimeters, right? Right in the middle. You don't have to calculate that. Now, make sure that if you have a different area here up top than what you have at the bottom, you do have to calculate y bar. It would change, right? It would not be in the middle. Okay, make sure you can do that as well. All right, so let's go ahead and shade. We have area 1 here. We have area 2 here. Those look really similar. And we have area 3 here. So we have 3 areas that we're working with now, okay? So if we want to find the moment of inertia about the x-axis here, okay, we're going to do 1 over 12 BH cubed, but area 1 and area 3 are the same. So 1 over 12 base times 20 cubed, okay? But now we need to take the moment of inertia of those two shapes and pull it to the middle, right, where we're trying to calculate the moment of inertia about this x-axis. This x-axis, by the way, is in the middle right here. So we need to pull those moment of inertias using parallel axis theorem. So we would have the area of the shape times 20 times our d value, which is 190 in this case, but we can just multiply this by 2 because there are 2 shapes. Then we need to add the moment of inertia of that second shape, 20 times 360 cubed, and we don't need to pull it to the axis because it already acts at the centroid. So this is our full formulation, and we get 511.36 times 10 to the 6. So just make sure you can recreate all of these problems and that all of these answers are consistent with the ones that you're getting. This really isn't that difficult. You just need to practice quite a bit, okay? Now, just to show you where I got the D's from here, to get D, again, you would take the middle of that shape, go to the axis that you're trying to find the moment of inertia about. If this whole distance is 200, we would subtract this thickness here, which was 20, so 200 minus 10 here, this is 10, would be 190. That's where we got the 190. And then, of course, we don't need to do anything with area 2 because the distance from the center of the area to the x-axis is 0. So my D2 is 0, and that's why we don't have to use parallel axis theorem for D2, only for D1 and D3. Okay?